Hello, good evening. Welcome again for the seventh session of seventh doubt session for the finite element analysis course. We start now and let others join meanwhile. So, until the last class, we had in the past week, week six, we had studied the Euler-Bernoulli beams, which are meant for which have an assumption of which are meant for the long beams, with an assumption that the normal planes would remain normal after deformation. But in this week, week seven, we studied the Timoshenko beams, which have a shear deformation involved with it, since the beams are thick and short. So, so we'll assume that the normal plane rotates by an extra angle psi, and thus the total shear strain would be given by this psi plus dw by dx. dw by dx would be our slope of deformation. So now instead of the normal fourth order equation that we had in Euler-Bernoulli, we deal with a coupled second or coupled second order differential equations with two variables involved. One is psi and another is the w. So in this week, we studied how to deal with this particular coupled differential equations, and uh, we can get the weak form just like the usual way. And with respect to the boundary condition, our first variable is w, so which is the displacement. So the essential boundary condition would be the value of w, and since to get the natural boundary condition term, we see the coefficient of the weight function in the boundary term, which is this term here. So this is supposed to be a natural boundary condition corresponding to our w variable, our first variable. And similarly, for the second boundary condition, we have the coefficient of the second natural boundary condition. We have the coefficient of the second variable here. And of course, our second variable is psi rotation. So the that essential boundary condition would be psi. So this ei d psi by dx is nothing but the moment, and this the other term. So we know that psi plus dw by dx is the strain, and multiplied by uh, g and a would give us the shear force. So we know the weak form of the problem, and we can get the boundary terms as well. So the problem here lies in choosing the shape functions. So as we saw in these classes earlier, just sorry, yeah, hello. So for this problem, we had two different weight functions, w1 and w2. So in choosing the shape functions, since w1 and w2 are independent, we can choose any different type of function for them, and the orders would be same. And so we started with the linear shape functions for this problem, and we dealt with certain problem that made the psi variable constant. So this essentially meant that the bending energy of the system should be zero, and we came to know that this problem is known as shear loss, which is a numerical issue. So to avoid this problem, there were two different solutions proposed. First one was to take different number of points or different order of the polynomials for the different shape functions. So if we take w1 as of the order 1, we can take w2 of the order So of course this would pose certain problem, as the different number of nodes would have the problem in assembling the different metrics and other vectors. So another solution to this problem is by considering one less point during the numerical integration. So we haven't came across to this numerical integration part in FEM problems. So at this moment, it's not very straightforward to understand this, but I'll just give a brief here that if we have some function given, some I'll just use this. So we can simply numerically integrate it by multiplying by certain weight function and acquiring the value of this function at certain points. So it's actually a summation. So as many number of these points I can be, so as high the value of n can be, the more would be the accuracy. So we have to evaluate it at number of different points, and if for this to resolve this particular problem of shear locking, we can just choose one less point for this particular shape function. So, for coupling the algebraic equations for coupled equation, we do the following thing. So, uh, we have the coefficient of the first variable in first equation. This is kij11, and we take this coefficient of second variable in first equation. Uh, and similarly, we highlight the coefficient of the first variable in second equation and the second variable in second equation, and we can merge them into a matrix like this. And here we distribute the variable in this order and the corresponding right hand side term. So this way we can deal with the coupled problems, and essentially we can deal with the uh, Timoshenko beam problems. So I'll just quickly move forward. So the next thing we studied this week was the eigenvalue problems. So eigenvalue is the characteristic of the system which is independent of any external influence. So it would essentially depend on material property of the system, geometry of the system, and the boundary conditions. But any external applied force would not essentially affect this thing. So representing so mathematically an eigenvalue can be represented as some function, of x, the variable. Sorry. So some function of the variable multiplied by is equal to some constant multiplied by some other function of the variable. So we'll see, for example, in case of an unsteady equation for bar, we can essentially express it in this form, where AU is equal to lambda times BU. So the omega square term here is our eigenvalue. So in most of the problems that we study in solid mechanics, eigenvalue is essentially the frequency of the system, but except for the buckling problems. So uh, just like other problems, we can solve for the eigenvalue problems using the finite element method. We can just take up the equation and get the weak. So just like any other finite element problem, we proceed by getting the weak form of the system of the equation. So we can express this equation here as in its weak form, and So we assume the solution as an interpolation of certain shape functions, and then we can have some other shape function for the weight function. So here this this first matrix is known as the stiffness matrix, just like the usual matrix we have. But the coefficient, there's another matrix which is the coefficient of the eigenvalue lambda, which we call as the mass matrix. Okay, so just like stiffness matrix, mass matrix is also symmetric, and we get some the equation in this form, just like the normal FEM, except we now have a mass matrix term involved. So for linear 1D element, stiffness, we already know that stiffness matrix looks like this, and the mass matrix looks like this. And in order to get the eigenvalue of the problem, uh, we we need to take the determinant. We need to get the characteristic equation, and that we can do by taking the determinant of k minus lambda m here. So this would give us some function of lambda, which is 0, and solving the roots of this polynomial would give us the eigenvalue of the system. So depending on how many nodes are independent nodes are there for this problem, we'll get different number of eigenvalues. So this was pretty much all that we covered this week, and I would wait if there would be any question, any doubts involved in the current week's content, and then we'll move forward. Okay, then we'll wait some more time to see if there's any doubt. Then we'll start with the problems. All right, then if there are no further doubts, then I'll start with the problems. The first problem is a steady state 1D bar is fixed at one end and is attached with a spring of spring constant k at the other end. Find the boundary condition of the problem and write the algebraic equation for two linear elements. So we are given a yeah. So we are given a bar, say some length L, and one end is attached with a spring. Oh, sorry, one end is fixed and the other end is attached with a spring. So okay, and the spring constant is k. Okay, then we need to find the boundary conditions and write the element. So first of all, what should be the governing equation of the problem? For 1D bar, we have following equation for the axial deformation problem. Okay, so it's steady state. We don't have time dependent term involved, and since there is no body force applied, you can say that fx is 0. We'll do that later. So first of all, what are the boundary condition of the problem? So we know that u at 0 is equal to 0. This is the first boundary condition. And what's the next boundary condition? So EA du by dx x equals to L is equals to, what should be the force here? Force should be whatever the displacement should be. So that should be equal to whatever the displacement here is, ULK. UL times K. So whatever displacement at this point x equals to L is multiplied by spring constant. So these would be the boundary conditions for the problem, and we need to write the equations for the system. So considering it to be a single 1D element, two noded 1D element, we have this element. This is node 1, this is node 2. So what is the expression for Kij here? So we'll do it for in terms of we'll do it for L. Okay. So this is dw by dx times A du by dx, and phi is 12w times fx dx. So for single 1D element, so for this element, the stiffness matrix comes out to be E upon He 1 minus 1 minus 1. Okay. So we have to consider two linear element, right? So similarly, HE for first element would be L by 2. 1 minus 1 minus 1. And similarly, we'll get the same for second element. So if we'll combine them, what we can get EA to EA by L, it's common. 1 minus 1 minus 1. This will be 2. 1 plus 1, 2. Okay. And this should be multiplied by the displacement at each node. Let's correct this. So our bar here is this. This is node 1, node 2, node 3, element 1, node 2. And so F would be 0. So we don't have any any body force. So F would be 0. And what about Q? So at first node we don't know Q. At second node we don't have any force here, any net force, and at third node we know that is U3 times K. So we can, so applying the displacement boundary condition, we know that at U at 0 equals 0, so we can put this to be 0, and then the reduce equation would be 2EA by L 2 minus 1 times U2. Side we have 0. You can further arrange this as 2EA by L 2 minus 1 minus 1 minus K U2 U3 0. Yeah, so this would be the system of equations for this problem. So can someone answer what should be the final solution of this problem? Do we have any volunteer to answer? Am I getting any response for this? Okay, I'll tell them. So since you'll see that the right hand side is completely 0, we'll get both U2 and U3 equals 0. So if you see the problem, post problem, we don't have any forces involved. It's just a simple bar kept at its place. So until and unless it is being held by any force, maybe any body force or some point force, there won't be any movement within the bar, and there won't be any deformation. So it would stay wherever, every point would stay wherever it is. So you'll get the whole every deformation at every point equals 0. So essentially our solution Ux would be 0. This is the solution for the problem. So this was just an exercise to understand how to uh, deal with the how to formulate the FEM problem and deal with different boundary conditions and get the linear equations. So anyways, we'll move forward if there are no doubts here. Okay, so now consider an Euler-Bernoulli beam with EI equals to 10 and length 1 meter. We have to develop the stiffness matrix and force vector and apply the boundary condition. So this is the given Euler-Bernoulli beam in the problem. So we'll just consider one element here. So first of all, the governing equation for this problem is fine. Okay, so we have, do we know the boundary conditions? We definitely know that W at 1 meter equals to 0, theta at 1 meter equals to 0. Since it's fixed at the right hand, you can see the symbol. And at the left hand side, we have shear, zero shear force, and we have some bending moment applied. Why? What should be the sign of bending moment here? Just a quick revision. Okay, do we get any answer? So since it's a clockwise direction, you'll have a positive 5. So this is the imposed problem, and we know how to get the weak form and the stiffness matrix term. We just write 1. Since anyway it is 1 meter. So we have square by, I'm sorry, this is d square w by dx square. Yeah, we have d square by times weight function v times ei, then a second derivative of the primary variable. Similarly, fi is given as v times fx. So since we know that Euler-Bernoulli problem, we use the Hermitian shape function. So we get 4 different shape functions corresponding the to displacement value at the nodes and to slope value at the nodes. So the stiffness matrix we'll get for one linear element would be EI upon h cube 6 minus 3h minus 6 minus 3h, and we have 2h square 3h, sorry, square, then we have 6 and 3h, then 2h square. Since we know the stiffness matrix is always symmetric, we can fill the rest of it down. Okay, so for this problem, what is the value we get? So h is 1, so we get k equals to 20 times 6 minus 6 3 6 3 minus 3 1 3 2. So this is a certain matrix, and what should be the force factor? There's no force applied, right? No body force. So it should be a 4 cross 1 matrix. Every term is 0. And we have a Q matrix. So at first node, what is the shear force value? It's 0. And at second, first node, the bending moment value is 5. Second node, we don't know. Third node, we don't know. Sorry, second node, the bending moment and shear force, both we don't know. So what would be the system of equations we'll get? Still need to copy it. No, I don't think. Times u1, u2, u3, u4. Sorry, u4. Don't need to write f. So anyway, 0. Q we can write. Okay. So how to apply the essential boundary conditions here? We know that u3 and u4 both are 0. So we can just eliminate these equations. Can straight away eliminate these equations. Then what will be left with? This, right? So should we try to solve this? We can. So for first equation, let's put it here. We have 6u1 minus 3u2 equals 0. And then second equation we have 20 times minus 3u1 plus 2u2 5 become minus 12u1 plus 8u2 equals 1. Can you solve this? Yeah, we just multiply this by 2 and add to the second equation. Get 12u1 plus, sorry, minus 6u2 equals 0. So this cancels, we get 8 minus 6, 2u2 equals 1, u2 equals half. And so u1 becomes, so when substituting this value in first equation, we get 6u1 equals 3u2. 3, that becomes 3 times half. 3, 1, 3, 2. So u1 is equal to 1 by 4. So these are the values that we get for u1, u2, and we already know u3 u4. So our solution for this problem would be, so ux or wx given by 1 by 4 times u1 plus 1 by 2 times u2, and u3 for already 0. So this should be a solution for the problem. Okay, there is no doubt here. This got a little complicated. So in real life, the equations are not so easy, and no, not the system is not so small. We have multiple equations, but to understand the problems, this is how basically the equations are solved. We get the variables and finally get the solution. Right? So we'll move forward then. Okay, then the third question is, consider the following coupled differential equation. Find the stiffness matrix for one linear element. Fine, can do this. So first thing first, we need to find the weak form. So we'll do for first equation. So first we write the weighted residue statement. So we have UV, I'll take W1 as first weight function. So we have square U by dx square plus V minus F times dx equals 0. So this integrating by parts, we get then we get this. I'll just write the boundary term later. W1 F here plus x plus we'll get minus here. So whatever it is. Further discretizing it, you can and write u equals to uj vj and w1 equals to vj. So this becomes sorry PL times t vj by dx times dx multiplied by uj. Here we have w1, sorry, we'll write phi here, and this is j. And then we have uj here, and we can just write this as pi times f times dx minus k, and write this pi. Anyway, we'll get to that later. So at the end, what equation we can get here is k11 ij times uj plus k12 ij times, sorry, this was vj. So similar discretization we can do for v, and we are doing for u. And then we have this fi terms. We'll combine all the terms here. So this is our equation 1, the equation corresponding to first equation. And second part, we can do the same. We need to get the weak form of the second equation. So for I'll do it here. Equation 2, we have the weight function here. We'll take v2 w2 here, t square v by dx square minus g dx equals to 0. So now doing the integration by parts again, we have dw2 by dx times dv by dx times dx. Now let's move it there. We have w2 times dx. So again, writing in terms of shape function, we get dvi by dx dvj by dx, and this should be multiplied by, this is b here, right, vj. And we have, so I'm just ignoring the, didn't write the boundary term here. We'll deal with that later. We get I times g, sorry, dx here. So this again, I'll just move it there. So what we get here, kij. So we don't have any coefficient for the uj variable here, right? So I'll just write it 2 2 kij 2 2 vj equals to f by 2, or to make a parallel with the first equation, we can consider 0 times uj plus kij 2 2 times pi 2. This is our second equation. Okay, so at the end, how do we combine the equations for multivariable problems? We just combine all the different Simpson matrices. So we have kij 1 1 here, kij 1 2 here, we have 0 here, we have kij 2 2. Since there's no u variable in the second equation, so we get 0 here. This should be uj vj and that's equals to fi1 fi2. Okay, so this is how the equation would look like. So for one linear element, can we write down the equations? So we have linear element. What do we have here? So ki, every ki is same, right? We don't need to worry about k here. We just keep the simple things up. So k is 1 upon he times 1 minus 1 minus 1. So we'll consider h equals to 1. And so this the whole sequence matrix can be written as 1 minus 1 minus 1 1. And same we have for the other one. If we are taking same shape functions, everything same, every ki should look same. 1 minus 1 minus 1. Here we have all zeros, so that's a zero matrix here. And again we have 1 minus 1 minus 1 1. And how should this look? So we have UJs first, right? So it's a linear element. You have two nodes, U1, U2, and then we have V1, V2. Okay, and then how should F look like? F is for linear 1D element. F is, I think, G upon He times something, 1, right? So we'll just write it like this. So since the function is different for each one, this should look like F for first one and G. Considering both are constant function. So this should be the final matrices and vectors. The final equation should look something like this. And we still don't know the boundary conditions. And of course, yes, we have to write the cube. So that's we don't know the value, right? Boundary conditions. So we have this set of equations where u1, u2, v1, v2, and q1, q2, q3, q4 are the unknowns. So can someone tell me how many boundary conditions do we need to solve this problem? I'll wait for the answer. Okay, since we are not getting any answer here, I'll tell you. So, since we have four unknowns here and four equations, no, sorry, not four unknowns. We have eight unknowns and four equations. So, there are still four unknowns that we can't get from these equations. So, for these four extra unknowns would be dealt with the boundary conditions. So, in total, we need four boundary conditions. So, and of course, if you see the equation, both are second order equations. So for each second order equation, you need two boundary conditions. So in that way, 2 plus 2 will get total four boundary conditions. Okay. So we need either two u values or one u or one the corresponding natural boundary condition to u. Uh, or we need two v values or one or two the natural boundary conditions corresponding to v variable. So yeah, so we can't get to the final answer here since we don't know the boundary conditions. But this should be the set of equations with all the variables. Okay, so now we'll head on to the next question. Okay, so we need to find the eigenvalues for the given stiffness matrix and mass matrix. So how do we find the eigenvalue? The characteristic equation. So characteristic equation is we get the determinant of k minus lambda times m. So this is the characteristic equation. Uh, from solving this equation, we get the eigenvalue, right? So let's try to solve this. K is 2 minus 1 minus lambda m. So lambda m is okay. So equal to 0. Sorry, determinant of this thing. So we have right here 2 minus 4 lambda, here minus 1 minus 2, then we have minus 2 here, then we have 1 minus 2 lambda. You take the determinant of this thing, right? So that's a simple 2 by 2 matrix. Pretty simple rule to take the determinant. We take 2 minus 4 lambda times 1 minus 2 lambda minus 2 by 2 minus 2 by minus 2 is 4 equals to 0. So solving this we get 2 minus 4 lambda minus 4 lambda plus 8 lambda square minus 4 equals 0. Okay, so what do we get here? 8 lambda square minus 8 lambda, and that's 2 minus 1 minus 2 equals 0. That's 4 lambda square minus 4 lambda minus 1 equals 0. So we can write this as 2 lambda minus 2 lambda minus 1 equals 0. Taking 2 lambda common here, 2 lambda minus 1. Okay, we can't do this. It's minus 4. So we just use the simple quadratic formula. That is minus b plus minus b square minus 4 ac, it makes plus 16, right? Minus 4 into minus 1, that's plus 4 into 4 16 upon 2a, that makes 8. So our lambda is 4 plus minus square root of 32 times upon 8. That makes, can further solve it. 32 is 2 to the power 5. So we can get it as 16 times 2, right? So 4 plus minus 4 root 2, right? Or 1 plus minus root 2 by 2. So we get two lambda values here. First eigenvalue is 1 plus root 2 by 2, and the second eigenvalue is 1 minus root 2 by 2. And we can get the eigenvectors also for this. If anyone wants, we can solve for that also. That's pretty much same. For getting the eigenvalue corresponding to lambda 1, we substitute the value of lambda 1 in the equations and just solve the equation to get the vector. Okay, so this much is fine. Otherwise, we'll move to the next question. Okay, so we'll consider an unsteady beam in problem 1. So we'll see what is problem 1. What can we do about it? Okay, we have K here. Okay. Hmm. So I'll not go into much detail. The governing equation and everything. So at the end, the matrix and vector equation we get in the end is times this whole thing multiplied by Ru, that is equals to F. And since we don't have any force applied here, this should be 0 vector. And at the end, what we need to do is get the determinant of this thing and equate it to 0 to get the characteristic equation, right? We have to take two elements, of course, so we'll see what we can do. So K is simple. What we got there is, I think this part was one. Here we have EA by L by 2, so 2 we got 2 EA by L. I'll just consider this thing as 1, so there won't be any trouble. And M is, I'll also consider coefficient here also 1, 2, 1, 2. This is M. So for two elements, if we combine K and M, what K, this is for K for element, M for element. So global K is 1 minus 1 minus 1 1, sorry 2 minus 1 minus 1 1 0 0, and similarly M global is 2 1 1 4 1 1 2 0. So if we combine the equations here, what do we get here? The final matrix is 1 minus K minus lambda M, right? So diagonal term would be 1 minus 2 lambda. Here would be 2 minus 4 lambda, and here it would be 1 minus 2 lambda. And what will be the remaining term? So minus 1 minus 1 would be minus 2. Here also minus 2. Also minus, sorry, also minus 2, and at the end we have zeros. So this is our k minus lambda m, right? And the the system of equation would be this matrix times u1 u2 u3, and here at the right hand side we have all zero. We don't know q1. Let it be. This is just the first problem, but with unsteady steady equation, right? So we have to consider unsteady here, and we need to find the eigenvalues for two elements. So two elements, we get three nodes, and now we'll apply the boundary condition. We know u1 that's 0, so we'll remove the equations, and then at the end we'll be left with what would be our k minus lambda m reduced. This is 2 minus 4 lambda minus 2 minus 2 1 minus 2 lambda, right? So in order to get the lambda values, what we need to do is get the determinant of this thing, k minus lambda m reduced, right? Then equate it to 0. So if you see, this is the same thing we did in the last problem. So the matrix that we got at the end was the same element, 2 minus 4 lambda minus 2 minus 2 1 minus 2 lambda, right? So that's the same thing. We'll solve, we'll get the characteristic equation as 4 lambda square minus 4 lambda minus 1 equals 0. Solving this, we can get lambda 1 equals to 1 plus root 2 by 2, and we get lambda 2 equals 1 minus root 2 by 2. Yeah, so this would be the eigenvalues for unsteady beam in problem 1. So I hope this was clear. So we are done with the fifth problem here also. Now I think we are out of time now. If there are no further questions, then we can conclude the session. No? Okay, then we'll finish this. So thank you for joining session, and I hope to see you in the next session as well, in the final section. Okay, thank you so much. Bye.